In this video, we solve problem 7.2.19-T from Essentials of Statistics, 6th edition by Mario Triola. The problem statement says a food safety guideline is that the mercury in fish should be below 1 part per million. Listed below are the amounts of mercury in parts per million found in tuna sushi sampled at different stores in a major city. Construct a 90% confidence interval estimate of the mean amount of mercury in the population. Does it appear that there's too much mercury in tuna sushi? So we've got a few data values, 1, 2, 3, 4, 5, 6, 7 data values. And we're asked to construct a confidence interval estimate of the population mean. So in order to do this, I'm going to show you how to do this first on my piece of paper, and then I'll show you how to do it in Excel. So let's do this on paper first. All right, now we know that our confidence interval estimate of the mean has this form, and this is x bar minus the error, and this is supposed to be x bar plus the error, provided that we have a simple random sample, and we will just assume that we have a simple random sample. And one or both of these conditions are satisfied. So n is either greater than 30 or the population is normally distributed. Now, they don't tell us this, but I would assume that the amount of mercury in tuna sushi is normally distributed. So provided that those hold, this is our confidence interval estimate of the mean. Now, we're not given the population standard deviation sigma. So we're going to use this formula where the population standard deviation sigma is not known. Now, x bar we can compute without knowing sigma. In this case, what we do is we use E equals this. This is our margin of error. It's T sub alpha over 2 times the standard deviation of our sample divided by the square root of the sample size. And we're going to have to use this two-student t distribution in order to find that t value. And the degrees of freedom are given by n minus 1. So we see we have n equals 1, 2, 3, 4, 5, 6, 7 pieces of data. So n equals 7. So let's write that down. Now, if I want to calculate x bar, remember how we do that? We just add all of the x's together and we divide by the sample size. So we'll have the sum of all of these values. And we're dividing by the sample size, which is 7. I'll use a calculator for that. I'll show you how to do this in Excel as well. It's much faster in Excel. So we've got 0.59 plus 0.74 plus 0.11 plus 0.97 plus 1.31 plus 0.49 plus 0.89. Add those together and divide by 7. And we get 51 over 70, which is approximately equal to this 0.73 or 0. Let's say 729 if I round to 3 decimal places. Okay, so that's our x bar. Now we just need to find the error. In order to find the error, we need the sample standard deviation. The sample size is 7, that we know, and we need T sub alpha over 2, where our degrees of freedom are equal to n minus 1. So I think what then I'll do next is I'll find the T sub alpha over 2. Degrees of freedom are n minus 1, which is 7 minus 1 in this case, so that's 6. So in order to find my T sub alpha over 2, I'm going to go to my table, and you'll have access to this during your exam. And you are looking for that table that involves the student t distribution. These are critical values of t for different degrees of freedom. Now, we were told that we want to construct a 90% confidence interval. So that means we want the confidence interval that takes 90% of our values and puts them in the middle. So that means we've got 10% of the area in two tails. I didn't draw it in a symmetrical way, but I'd have 5% in this tail and 5% in this tail, which can be converted to 0.05 if you want that in decimal form. Okay, that's important. And it's because we have a 90% confidence interval. We've got the area in two tails of 10% or 0.10 in decimal form, or the area in one tail of 5%. So we go over to our critical t values chart, and we have the degrees of freedom 6, and then we'll find the appropriate critical t value over here. And in order to decide which column we're in, we have to either look for area in two tails or area in one tail. Well, we saw from our picture that if we have a 90% confidence interval, the area in one tail is 5%, so we could use this column. Or we can think of it as area in two tails is 10%. We're still in the same column. So whether you use the area in one tail or two tails, you're going to end up in the same place. And then we want to go down to the degrees of freedom of 6. So we're in this column, degrees of freedom 6, and the critical t-score, t-value, is that 1.943. So this is t sub alpha over 2 is 1.943 for that sample size that has n equals, for that sample size of 7 with degrees of freedom 6. Okay. So now I've got my t value, I've got my n. The only thing I need to compute now is the sample standard deviation. We actually know what xbar is. It's this 51 over 70. Oops. Now, if I'm going to calculate a sample standard deviation by hand, and this is pretty unusual, but we can do it. We can use these formulas that we learned about way back at the beginning of the course, back in chapter 3, I think it was. For sample standard deviation. Now, if I go here to my table, this is the same table that you'll have access to during your exam. Trying to find that page that has the formulas on it. There it is. Okay, right here, we've got formulas for standard deviation. This is the one that probably makes the most intuitive sense. You take x and you subtract the mean. That's a deviation from the mean. You square those. And then you divide by the sample size minus 1, and you take the square root. Now, we said that this was actually easier to compute in practice. I would normally do that, but I've already computed the mean. So this one really isn't that bad this time because we already had the mean and we needed the mean because we're finding a confidence interval for the population mean. Since we already have the mean, I think I will use this top one. So I want to take each x value and subtract the mean. And in this case, our mean was that 51 over 70. So I've got 0.59 minus 51 over 70. And then we're going to take all of those and square them. So I have 0.74 minus 51 over 70. 0.11 minus 51 over 70. And you just keep going. I don't know, every once in a while I'll put a little line through my 7. I don't have to though. You know, we don't have to, but sometimes I like to do that. And again, the formula for sample standard deviation is this, or one of the formulas. So we want to take these guys and we want to add them up. And I don't think I will do those calculations by hand. I'll do them in my calculator. So I've got open parentheses 0.59 minus 51 over 70, close parentheses and square it, then add 0.74 minus 51 over 70, close parentheses and square it, and then add 0.11 minus 51 over 70, close parentheses and square it, and then add 0.97 minus 51 over 70, close parentheses and square it. So that's that one, plus 1.31 minus 51 over 70, square it, then 0.49 minus 51 over 70, square that as well, add 0.89 minus 51 over 70. Oh, look, I don't know if it'll let me. Looks like it's saying you've run out of space. So I'll delete that and delete that. And this is going to give me all of those except for this last one. So I'll say equals. I didn't like it. Let's try again. 0.59 minus 51 over 70. Sorry about this. It's taken a little longer than expected. Plus 0.74 minus 51 over 70. Square it. Plus 0.11 minus 51 over 70. Plus 0.97 minus 51 over 70. And I'm squaring each of these as I go. I'm not saying that I'm squaring them, but I'm squaring them. Plus 1.31 minus 51 over 70, square it. And then we add 0.49 minus 51 over 70, close parentheses and square it. Last one, plus 0.89 minus 51 over 70, close parentheses and square it. And that leads us to this value, 6,169 over 7,000. Okay, so now we're going to take that and we're going to divide by n minus 1. N was equal to 7, so n minus 1 is equal to 6. Let's take that answer, divide by 6, take the square root of the answer, and that is our sample standard deviation. And I'll round to 4 decimal places. Okay, so we've got our error is equal to this critical t value, which we found earlier using our table. We just computed the sample standard deviation and we've got our n, so we can substitute all of those into the formula. E equals this. So that's 1.943, that was this, times approximately 0.3833 divided by square root of the sample size, which was 7. And I get an error of approximately 0.28145. So I guess I would round that to 5. Okay. So we've got our X bar, and then we've got this. Actually, since I rounded that other one to 3 decimal places, I'll round this to 3 decimal places as well. So we'll have that. It was a 4 before I rounded it up to a 5. And then I want to add and subtract the error from this. So X bar plus the error is my upper limit. And then X bar minus the error is my lower limit. Okay, so we've got 0.729 plus 0.281. We get about 1.01. And then 0.729 minus 0.281 equals 0.448. So those are my upper and lower bounds for that critical, or that confidence interval, excuse me. Okay. Now let's see if my lab statistics likes it. So I'll go back to the homework now. We're asked to round to 3 decimal places. Hopefully I didn't round too early. All right, it likes it. Now, before I go on to the next part of the question, I want to show you how to do this in Excel because it's much easier in Excel. Before we answer that, let's go here. So I'm going to say yes, let's open in Excel. Sorry about that. I tried to change to Excel and the screen sharing on, what's it called? The screen sharing on Zoom didn't like it. So here's our X values. If I want the mean of this sample, I can just say mean of all of this. Oh, actually, it doesn't. The command in Excel is not mean, it's average. I'm sorry. There we go. 0.7285, and that's what I got over here on paper, 0.729. And then the standard deviation, I'll choose ST, standard deviation for a sample. And we want this to be our sample. And we got 0.383. And notice that, I'll stop sharing for just a moment. Notice that that's the same thing that I got when I did this calculation by hand. So the hand calculations and Excel are agreeing, which is fantastic. Okay, and now we just need the student T distribution. Now, in order to find the critical T values, basically we're looking for T values associated with a certain area. Remember, if we want a 90% confidence interval, we want 10% of the area, but we want it split into 2 tails. So what we're going to do is we're going to use a T distribution, but we want to do it backwards. We know that we want 10% of the area in 2 tails. So we'll do T, and notice that there's options down here for T dot inverse dot 2T. That's for the inverse of T with 2 tails. And then the first thing it asks you for is the probability in the 2 tails. So we want 0.10, that's that 10% of the probability, that area in the 2 tails. And then it wants the degrees of freedom, which is 6. The sample size was 7, so the degrees of freedom was n-1, which is 6. So we get 1.943. Now let's go back to that paper. The paper I was showing you earlier. Look, I have 1.943 here. So you can use the table that I'll give you during the exam to find this critical value of T, or you can use this function in Excel. And it was T, actually, let's go back to that Excel sheet. Sorry, here it is. I'm not sure that I'm sharing my screen right. Share the screen. So the function that I used here was T dot inverse INV dot 2T for 2-tailed. So we use this function in Excel. In order to get this T value. And it asks for 2 things. It asks for the probability in those 2 tails, which is the 10%, and then it asks for the degrees of freedom, which is 6. We got exactly the same answer using Excel that we got with our table. Okay, so now let's go back to Excel. So this down here, that's the mean, or the sample mean. Oh, sorry, I don't want to have equals there. So that was the sample mean. And then this one was the sample standard deviation. And this was the critical t-value from that student t-distribution. Okay, now the upper and lower bounds, well, let's find the margin of error first. The margin of error is equal to that t-score. So I want the t-value times the standard deviation, sample standard deviation is right there, divided by the square root. Use SQRT in Excel of the sample size, and the sample size in this case was 7. So you can either type that directly or you can count the values. So I can say the count of values from here to here. So that's going to count those for me, and it's going to tell me that my sample size is 7. And that gives me the margin of error. Now that is the same margin of error that I got when I did this on my paper. I just want to show you again to get the same value. So now I want to take the sample means, and I want to add and subtract the error. I'll do that in Excel. So my upper limit is the sample mean plus the error. Oops, having a hard time with that. So I guess it's too close by, so let's do it here. I want sample mean plus the error. And then the lower limit, I want it to be the sample mean minus the error. And so we get 1.01. And if I'm rounding to 3 decimal places, because that's what they asked us to do, we get that. And 0.447. And I believe due to rounding, I got 0.448. But it was close enough to what I got when I did all of these calculations by hand. So you see that we get exactly the same thing. We're very, very close to the same thing. But we're going to be slightly more accurate when we're using Excel, because that t-score is approximated to more decimal places. The sample mean has the entire sample mean approximated to more decimal places, and the standard deviation is also given to more decimal places. So it's just more accurate all the way around when we use Excel. Okay, now the question says, does it appear that there is too much mercury in the tuna sushi? Well, remember what the food safety guideline says. At the beginning of the problem statement, it says, the food safety guideline is that the mercury in fish should be below 1 part per million. The question is 1 part per million in this range from 0.448 to 1.01? It sure is. Yes, it does appear that there's too much mercury in the sushi, because the mean amount of mercury in the sushi is supposed to be lower than 1 part per million. And it looks like there is a possibility that the mean could be above 1 part per million. So we're going to say the answer is no. And it's because it is possible that the mean is greater. It is possible that the mean is not greater than 1 part per million. Also, at least one of the sample values is less than 1 part per million. So at least some of the fish are safe. Now, is there too much mercury in the sushi? The answer to that question, I'm sorry, I was asking myself the reverse question. Is there too much mercury in the sushi? The answer is yes, because that food safety guideline is not being met. So yes, it is possible that the mean is greater than 1 part per million. At least one of the sample values exceeds 1 part per million. We've got that 1.31. So at least some of the fish have too much mercury. So that's our answer. That's how we solve that problem.